All right. Welcome. Good evening, everyone. Welcome to the session 12. Session 12 is related to the climate change and building design. And we have three presentations. We can start with the first one with the team project title, Review of Building Design. It's different title from what we have. Okay. Review of Building Design Case Studies in Oman and Opportunities of Using Artificial Intelligence and Internet of Thinking Technologies for Thermal Comfort and Energy Efficiency. I think Ahmed Al-Badi will present the
we will
the call. By the way, for the record presentation will be delivered later to the audience. Also, if you have any question, please highlight it in the question and answer panel. And after all three presentations, we have time to answer the questions. Thank you very much. Start. Okay. And welcome to Dr. Nadal Timimi, is also sharing the session with me.
Thank you very much, Dr. Abdullah.
Good evening, Dr. Nadal.
Many thanks. Very good evening.
Thanks. Okay. Welcome. Welcome. Thank you very much. Okay. Thank
you. Okay.
Please start. You have 15 minutes. Okay, from now.
Thank you, Dr. Abdullah and Dr. Nadal, for sharing this session. So, hello everyone, and welcome to this presentation where we try to review certain building design cases in Oman and also review the opportunities of using AI and IoT technologies for thermal comfort and energy efficiency. So actually this work is a result of a discussion between myself, Ahmed Al-Badi, and also my colleague Ahmed Al-Ghdani, who's been doing research and also actually applying artificial intelligence for different applications, and Yang Zhang, who is a professor of combustion and energy at the University of Sheffield. So we'll start with the outline, and initially I'll try to answer why we actually need to consider the emerging technologies. Then we will look at the previous research and what we actually have learned from it and how we can take it to the future. And then we take the topography influence on buildings in Oman, and then we ask the question, have we actually used that kind of knowledge? Then Ahmed Al-Ghdani will kind of go through the what's called the comfort-driven and energy-aware system. He will then show us some examples and then present an implementation framework. And at the end, we will leave you with some questions to think about. So why do we consider such technologies? New buildings development have usually significant opportunity available to improve them, and that's through the design itself. It could be also through any of pre-planning what kind of passive methodologies for thermal comfort and energy efficiency. However, that chance is not available with the existing buildings, and usually it's much more challenging. We can also, it could be expensive if we would like to improve some radical changes. And so we think by analyzing the human behavior factors and occupancy patterns, we can actually improve the performance of existing buildings. So this is what we try to do, is try to think about the existing buildings, and then maybe we can take that knowledge in the future. So how about the past? Yesterday, John Norton actually presented of what I can call a historical snapshot when he did his research in 1975. And he and his colleagues actually traveled throughout Oman, and they presented the methodologies that people actually use in their houses. And one of the profounding, I think, things that he presented is this photo that was drawn by Salem, who used to live in Nizwa, of his home. And it turns out to be completely different, image. The thing that he drew was completely different from his actual house. And now we ask the same question. When we look at that past research and our current building development today, we ask the question, where do we want this to lead us in the future, given all the issues that we currently got in Oman, for example, including the energy prices, but also the other issues such as the natural disasters and the cyclones. I think people can agree on this, that the modern development of buildings in Oman have not adhered to energy saving principles. This is said again and again in different reports in the 80s, in the 90s, and even in some of the proposals at the end of John Norton report. And this has actually happened despite the success of the vernacular architecture. And we kind of think that ignoring the same principle again and again will just lead us to these financial burdens, and we will reach a way where it actually becomes a risk, and that's what we have to think about. We currently now know that in general, Oman has 4 different regions in terms of microclimates. Those are the coastal, the mountainous, the southern, and the desert regions. In this map, we actually we've reproduced, so that's now in color, and it actually shows also the population density around these regions. And the past research actually also shows that the vernacular architecture has different kind of methodologies to deal with that microclimate of these regions. And now have we used this understanding of the evolved methodologies or actually ignored them? We can now give an example of the school or the public, the state or public schools in Oman. So we think that actually this is a piece of evidence that the local environment or the microclimate is not actually taken into account, because there are over 1,600 schools and they all follow the same design. So is it true that this is actually based on actually trying to understand the climates of different regions, or we have decided to build them exactly the same way everywhere? The other thing that actually some people now are even trying to change by education is the fact that if we continue with this idea that we need to keep designing or even building the same based on the same design, then we're actually taking away this incentive to innovate, to change, because at the end of the day, we do have to change and to improve the performance of these buildings. So in the paper itself, it actually gives more discussion on the classroom layout, the behavior of teachers and students throughout a typical day. And that's where we actually we can conclude that even sometimes the function, I mean, the layout and then the building itself is not actually fit for the function it's supposed to be. On the other side, we also have seen these promising initiatives. So this one is actually an initiative by the Research Council of Oman that started in 2011 to design and build eco-friendly houses, which resulted actually, you can take that knowledge into practice. It resulted in some houses. So on the right here, we can see just 2 examples by the German University of Technology and also the Sultan Qaboos University. And so we agree with Professor Nicholas Campbell that he says and explains that actually this kind of initiatives breaks the stagnation. It is a stagnant kind of culture and behavior, and it has to be changed. We do have to kind of stop and think. And this kind of initiatives, it doesn't have to be stopped. It doesn't have to stop here, but it also can accompanied by promoting energy utilization, design methodologies by the government, by the industry, but also implementing this with the, in education courses. I think I'll stop here for now, and then Ahmed will lead you on the use of data and actually why we need data and how we can take that into practice for current developments and buildings.
Thank you, Ahmed. The main need for data comes from the fact that to be able to evaluate the building performance and the design performance from a thermal point of view as well as from the energy efficiency point of view, you will need to gather data to be able to evaluate it properly, especially this data will be different from region to region, as you have seen in the previous slides. And this kind of data right now in Oman, we don't have it really accessible to the public. Usually we'll have to contact certain bodies such as the airports or certain organization to be able to have access to this kind of data. So that's one thing. And when we look at this, if we go to the next slide, we can see that we have 2 rising or emerging technologies that can really build upon and improve the current situation to be able to drive comfort-driven and energy-aware systems. And that is mainly using machine learning as an optimization tool to be able to set the parameters properly for our heating, ventilation, and air conditioning systems. And this data that we're gathering can be easily gathered through an Internet of Things system, which is basically a network of different sensors in a specific layout to be able to get the really reliable and close to real-time data. And if we look at the next slide, we can see that we're having several factors that actually affect our thermal comfort. And there might be even more than what we see, for example, in the figure we have, ranging from the activity level to the temperature itself in the ambient outside, what am I wearing? So all of these factors need to be put into a mathematical representation, and this mathematical representation needs to be really accurate, and it needs to fit the kind of techniques that we're using, which we'll discuss also on the next slide. But before even that, we have two models that have been, like we see here, the PMB and the PVD models. These are basically an indexes to the occupancy map and the thermal comfort of an individual inside a building. So,
excuse me, Dr. Ahmed, excuse me, you just have 2 minutes to end up the session.
Sure. So we can see that air has been used as an optimizer in one of the applications. And additionally, it can be used has been used as a predictive control to define the temperature ranges based on historical trends for the data and the seasons. And most of the architectures that we've seen has been used are those architectures that have temporal features that can actually adapt over time. And if we see to the next, we can see that bringing such a system, it's similar to the analogy of PID controllers. We can have a controller that is based on neural network with the benefits of having weights and biases to be able to optimize it even better. Lastly, this can give us a system that can give us something like a heat map for the occupants, and then be able to target the active zones and zones where we actually need to control the heating, ventilation, or air conditioning systems. Combining all of that, we have came up with a framework that we believe can help implementing such systems, from the layout of sensor to the kind of data you can get and the insights to drive the control systems of heating, ventilation systems. Reaching to the end of our presentation, we have few questions that we believe can really put a spark to our great discussion. Are we actually applying the research and the understandings that we're getting out of this research in building development in Oman? And how can these results and insight be communicated to the relevant parties, whether it was government, education institutes, or industry? And can we make this communication even faster? Thank you for your attentive listening, and looking forward to your questions and discussion. Thank you.
Thank you very much for your presentation, and the question will be at the end of the 3 sessions. We can go to the second one. I cannot pronounce the name exactly.
No problem. So my name is Eusébio Conceição.
Okay, welcome.
I can start my presentation?
Yeah, please start it and upload it. Okay, so we have the second presentation. This is about numerical study of smart HVAC system using human thermal physiology control. And you have 15 minutes to present your work. And later on, we have after finishing the presentation, we have a question. We have another presentation. After that, we have the question panel. Please go ahead.
You can see my presentation now? It's okay?
Yes, we can see this. Yes.
Okay. So thank you very much for your introduction. My name is Eusébio Conceição, and I will present this work entitled Numerical Study of a Smart Heat Ventilation Air Conditioning Systems Using Human Thermal Physiology Control. The work is developed in the University of Algarve with collaboration with the University of Reading. So the main objectives is to develop a smart heat ventilation air conditioned systems using the human thermal physiology control. The traditional systems use the air temperature. In this case, I use the human thermal physiology as control in order to guarantee the better comfort levels in the occupied spaces. So I will analyze the influence of different heat ventilation air conditions powers. I evaluate the thermal comfort in order to control the systems, and also I will evaluate the indoor air quality in space, because it's very important to guarantee thermal comfort, but it's also very important to guarantee indoor air quality. So the first step, I will present the numerical model. It's a numerical model, a software developed for my team during the last 10 years, and simulate the building, the occupants, and the CFD. It's a complex software. So I will show the building and the human thermal response. The building is divided in 3 parts: opaque, transparent, and interior bodies. Is considered all the heat exchange between convection, conduction, generation, mass transfer, with renovation, transpiration, and radiations. So we consider a great group of the thermal phenomena. In the opaque surfaces, all the opaque is divided in different slices. It's very important to guarantee similar the temperature distribution inside the opaque surfaces with similar with the reality. So another part is the transparent. In the transparent surfaces, it's possible to consider one transparent surfaces or more than one transparent surfaces. The first pictures, I show the example of, I use the incident, the reflections, the emitted, the absorbed, and the transmitted radiations. So the numerical software consider all the transparent surfaces, consider all these phenomena. However, there are more complex transparent systems that I show in the second pictures, as the ACF duplicate facade that is built with more than one transparent surfaces. So this is more complex situations that the software consider also in the numerical simulations. Another part, very important, is the radiations. The radiations is very important to calculate the external solar radiations and the internal solar radiations, and also the heat exchange between radiations for each space. So in this case, is the numerical software consider the solar radiations during the day, and consider in the outside and inside the space all the shading device that's used considered in the numerical simulations in order to guarantee a calculation of solar radiations for each opaque or transparent surfaces, similar to reality. After, another part important is the equations. In the order to make the simulations, is necessary to introduce energy balancing equations and mass balancing equations. All the equations is resolved using the Range-Coulter with error control. It's very interesting resolution systems, because they increase the time and reduce the errors during the simulations. So in order to develop the equation systems, I use a philosophy, use a design, the CATE, computer aided design. All the building is designed in the computer, and after the computer itself, using the design, generate all the equations. For the opaque surfaces, generate all the energy equations. For the transparent surfaces, inside the spaces, and generate also the mass equations that will very important to calculate the carbon dioxide concentration, water vapor inside the space. That is used to evaluate the indoor air quality. So in order to evaluate the thermal comfort, the numerical software simulate the human body thermophysiology. Consider the occupants divided in different spaces, in different elements, and all the variables are considered. In general, the heat exchange between the human body and the surrounding surfaces is used to evaluate the PMV. That depends on different variables. As example, the air velocity, mean radiant temperature, relative humidity, air temperature, clothing level, and activity level. And other, like radiations, is also considered in this case. So, in order to guarantee thermal comfort, the international standards divide in 3 parts. For me, it's more important that using this work, the category C, in order to guarantee that all peoples, the predict percentage of dissatisfied peoples is lower than 15%. In this case, the PMV predict mean vote change between minus 0.7 to 0.7. So minus 0.7 is very important in winter conditions because there are low powers is used in this case. And for summer conditions is used the PMV equal or lower than 0.7. In my case, I will show one situations. I use the PMV lower than 0.7 because it's winter conditions. Summer conditions, sorry. So then the numerical software, there are a group of inputs, another group of outputs. There are as input, there are a geographic location of the building, evaluation of surrounding variables that can calculate numerical or experimentally for the air temperature, air relative humidity, wind velocity, wind directions. The carbon dioxide concentration is also very important. The geometry of the building use the CATE, the thermal property of the buildings, the occupancy cycle, the clothing and the activity levels, and the air ventilation topology using during the day. So the output is all the coefficients, the radiations, air temperature, air relative humidity, air velocity, carbon dioxide, thermal comfort, power, and air quality. So it's a group of situations. In this case, I use experimental chamber, similar to the experimental chamber that I have in my laboratory. There are a small chamber with 3 windows, turn to south, and I will analyze 3 kinds of situations. The first one without heat ventilation air conditions, and the second one with heat ventilation air condition with a middle power, and the 3 situations is using the heat ventilation air conditions with higher power possible. So the chamber, I will show the dimension of the chamber. There are 3 windows turn the south. There are occupation cycles because the people enter and leave from the space during the day. I use summer situations with Mediterranean conditions. The occupant activity is 1.2, and the clothing, typical summer clothing, with 0.5 clo. I use the input or the air temperature, relative humidity, wind and velocity and directions for typical winter summer day. As results, so here you can verify the evolution of temperatures during the day. You can see the first level is without control, higher temperature. The second layer, you can see the external temperature, and green and yellow, you can verify the evolution of temperature with control. When the space is occupied, the temperature is controlled. However, when the space is not occupied, the temperature is not occupied. You can see the beginning of the day, the lunch time, the two space where the people are not in space, and the final of the day. So here you can verify the evolution of temperature. After, I will show another parameter used to calculate the thermal comfort, is the mean radiant temperature, that is calculated by a numerical model, because it's very important to control the temperature, and you can verify there are higher temperature without control, but two small temperatures evolutions when I use the control of the total control of the power of 100% is yellow. That is very important in this case, but in green you can verify the other situations with the middle of power. Finally, I'll show you the evolution of PMV. The first line, the higher with higher temperature, is evolution of air temperature without control. It's not acceptable. However, the two situations, it's their guarantee PMV near 0.7. It's acceptable value for winter, for summer conditions, and acceptable for the category C of the international standards. So you can verify using in yellow. When I use a power with the maximal power, with the 8 ventilation air condition with maximum power, the thermal comfort is guaranteed is lower than 0.7. However, when I use a middle power, you can verify that the PMV in general is around 0.7. However, in sometimes there are small, a little higher than 0.7. So in yellow situations, we use a power, a maximum power, I can verify during the day thermal comfort acceptables. To conclude my presentation, I'll show the powers that I use in my simulations, the higher and the middle, when the 8 ventilation air conditions work. So this is the representations of the powers. And in conclusions, in this study, the 8 ventilation air conditioned systems with error control based in PMV index was evaluated. 3 case studies were analyzed off and power limited to the middle of a total of its maximum values. The PMV control systems guarantee improvements on thermal comfort level acceptable by positive PMV values and thermal comfortable hours decrease. The control systems, the seconds with the maximum power, guarantee better levels of thermal comfort for the occupants and less uncomfortable O-rings than the system 1 with the middle of the power. The lower thermal energy consumption is obtained in the control system 1, and the control system 1 guarantee the best compromise between the lower energy consumptions and acceptable thermal comfort levels. In the future, I use my university. I have different buildings using in CAD systems, and I apply this kind of systems in the different buildings in order to guarantee the better comfort of the occupants. Thank you very much for your attention.
Thank you very much for this nice presentation. I will lead my colleague, Dr. Nidal Al-Tamimi, to introduce the third presentation and team.
Okay, thank you very much. The second presenter, I don't know whom.
The third
Dr. Sayed Shah?
Yes,
Dr.
I'm
Sayed
here.
Shah is available?
Can you hear me?
Okay. Yeah, could you please share your presentation?
Sure. Share screen. Can everyone see my slides clearly?
Just to max. Okay, fine. Okay, Dr. Sayed Zain
yes.
Shah, maybe. He's the last presenter today in this session. His topic is accessing the thermal comfort for the elderly using non-contact skin temperature measurements. So floor is yours, Dr. Said. Most welcome.
Thank you so much. Would you like me to start presenting now? So shall I start presenting now? Apologies.
Yes, please start.
Thank you. Today I'll be presenting work done by myself and my co-authors, Dr. Yijing and Dr. Fan Wang, on assessing the thermal comfort of the elderly using non-contact skin temperature measurements. Outlined below will be the areas which will be discussed during the presentation: the introduction and background, methods used, results and discussion, conclusion, and the limitations and further studies. The aim of the study was to determine whether the overall thermal comfort of the elderly can be predicted using non-contact skin temperature measurements. Many studies using skin temperature measurements have been conducted on young adults in climate chambers. This study, however, involved the elderly and older adults in familiar living environments. The elderly are the fastest growing demographic in the UK and expected to represent 24% of the population in the near future. Many are, however, unable to adjust their thermal environment due to loss of autonomy from age-related illnesses such as dementia. And many of the building regulations are based on research conducted on young adults and their requirements. However, recent studies have shown that the elderly prefer warmer environments, and as they spend 90 to 100% of their time indoors, it's important more research is conducted into their needs and requirements. So what we built on to help us construct the project was that studies have already shown that skin temperature measured from the hands can predict thermal comfort to a high accuracy. Thermal imaging can take accurate measurements from a distance, minimizing disruption and distress to users, and that studies have found skin temperature is not affected by relative humidity under normal room temperature. All of this combined opens the possibility of designing a personalized comfort model with minimal user input. 2 studies were conducted for this research. The first involving 7 retired elderly residents from the Line of Court Care Home in Edinburgh, UK, aged over 70, 5 older adults working from home in individual home offices in Northern Sweden, aged 45 to 75 years old, and in both studies it was mixed gender participants. Objective variables were measured from the occupants in their rooms, and subjective indicators of thermal comfort from the occupants using a questionnaire based on the ISO standards shown below. The measurements were taken during the participants' daily winter routine in familiar environments, and everything was done to minimize stress or affecting how they do their day-to-day activities. Contact was minimized, with measurements taken at a distance out of the patient's line of sight. Room temperature was increased over time in the home office study in Sweden. However, the same was not done in the care home study due to concern of the change in room environment would do so for the elderly participants. No restrictions were put on the participants, but both were advised from refraining from food and drink consumption during the measurements being taken, and also limiting their activity to do. In the questionnaire, 3 questions were asked to the participants. First being their thermal sensation vote. How do you feel about the temperature at this precise moment, using the scale below, from cold, -3, to neutral, and then hot. And then thermal satisfaction. How do you find the room temperature using the scale below, from 0 being comfortable to -3 being uncomfortable, and also the thermal preference. How would you prefer the room temperature to be using the scale below, from much cooler to much warmer? You can also see below the equipment that was used for the study. We used a data logger, which was placed in the room away from any equipment which would interfere with it, and also in any way where it would affect the participants. A thermal imaging camera shown below was also used to take the readings. So here's the results. As you can see, the hand temperature to room temperature has a strong linear correlation, with in the home office study with the older adults being an R value of 0.77, and for the elderly in the line of care home, an R value of 0.62. The elderly were not restricted and wore clothing of varying insulation values and performed light activities. And this likely counted for the lower R² value compared to the home office study, where the older adults were restricted due to working requirements, stationary at desk and wore light office clothing. The lower room temperature required for the elderly to have the same hand temperature as the older adults is likely due to them having warmer clothing. This also links with Olson's study that had similar correlation but required a much higher room temperature to reach the same hand temperature as the participants in both my studies. And this potentially is the reason being his participants were naked, wearing far less clothing. With the thermal satisfaction vote, the room temperature was found to be having a higher correlation of an R² value of 0.14 compared to the R² value of 0.74 in the home office study. And this is likely due to participants being aware that as time went on, the room temperature was increased. Chowdhury's study, participants had a range of clothing insulation values and no correlation was observed. And this is similar to the elderly in the line of care home study. Wang's study showed participants wore more warm clothing and required a room hand temperature of only 30 degrees to feel firmly comfortable in comparison to the home office study with the older adults, where it required a higher temperature and they wore lighter clothing. With the thermal satisfaction, the preference for room temperature was in line with building regulations of 20 to 24 degrees, but at the higher end. Hand temperature was found to be a better indicator of thermal satisfaction, and a hand temperature required for thermal comfort for thermal satisfaction was also in the same line as the previous things studied in the home office study with the older adults. This pattern again is seen in the thermal preference, with hand temperature being a better indicator of thermal preference compared to room temperature, and again the participants preferring a room temperature on the higher end of the building regulations. So, summary of the findings: the hand temperature measurements through a non-contact method was significantly correlated with room temperature. Clothing level had a significant effect on hand temperature and subjective thermal comfort and their correlation to room temperature. The hand temperature was significantly correlated with room comfort and when the participants had the same clothing insulation level. So to conclude the findings, the research suggests that hand temperature measured by non-contact methods could be an indicator of thermal comfort for an occupant if the clothing level factor is applied. The limitations of this study were due to the small sample size, COVID-19 restrictions limiting what could be done, the lack of detailed recording of the clothing worn by the participants, and the study being at an early stage. In a future study, we'd like to build a better model for predicting thermal comfort in an older population. With a larger sample size, would be required to do so, and a clothing factor applied along with it. The future application of this model is that it could allow a smart heating system to achieve automated control of individual comfort and energy efficiency by tracking the palm of the hand, clothing, and movement of the occupants, creating improved quality of life, especially for users with limited autonomy. Thank you for listening to my presentation.
Thank you very much. Maybe we can start the question dinner. Should we start at 5 o'clock, but we have some few minutes. So I will start with the presentation number 1. There are a few questions. The first one, does Oman have the infrastructure and capabilities to implement such new technologies اللي هو الانترفيس Internet of Things and artificial intelligence?
Yeah.
You can answer later.
Yeah. So the infrastructure is there. First of all, let's just think about the IoT. So these are the hardware that needs to be actually implemented in buildings. So although it might be like difficult to do that in the current, the houses, but it is much and way easier to do that, for example, in corporation and also large residential places, large, apartment buildings. it's much easier to do it that way. But then when we think about how to actually utilize that data, then here we need to that also needs to be led by the research at the universities. And it will end up being a collaboration actually between everyone. Now, you can use it obviously for many things. For example, you can talk about the dynamic behavior. Now, every building is dynamic. People move around that place. People switch on and switch off things. So their thermal comfort requirement is different from one part of the building to the other. And so it's dynamic. That's the idea of getting those kind of information. You can also optimize the mechanical means, but also you can end up with the prediction, for example, of the occupancy patterns in a building. And I think everything is there. But it needs to be at the end kind of a collaboration between different parties. Like Professor Susan mentioned yesterday, is if this kind of thing, because it's kind of a benefit for the country itself and how we're actually going to live and develop buildings in the future. And so you can't actually do this because you need some profit out of it at the end, because that will not lead you to the right way. And so the benefit of this should be actually optimizing the energy use and improving thermal comfort and finding the best spot between those two.
Okay, thank you very much. The second question is, if you implement such technology, what about the effect on the energy consumption?
Okay.
Do you have some study or some estimation about energy consumption?
So in the paper, we actually do refer to some studies where people use different kind of techniques. And Ahmed Lodani can actually mention a little bit more on this.
All right. In one of the case studies where they actually implemented an artificial neural network to actually control an HVAC for one of the buildings, in one of the case studies that we have reviewed, they managed to achieve around 40% improvement in the energy savings. So that is one example. And there is really another example from a neighboring country. It was done in Saudi Arabia, actually, where they used IoT data loggers to actually be able to monitor or measure the energy consumption with respect to the ambient temperature outside, and to be able to come up with some metrics, let's say. And that metric was actually the ratio of windows to walls with respect to the building orientation. Where is it facing the sun? And they came, for example, to a conclusion that has been further communicated to the Ministry of Housing at Saudi Arabia, that buildings that have a window to wall ratio of less than 15% can achieve around 40% as well reduction in air conditioning bills. So there is really promising case studies and implementation that we like, even from neighboring countries that kind of share a similar climate to Oman.
May I leave Dr. Nadal? He can highlight the question to the second presenter.
Can I add a comment, please?
If you don't have it, I can continue, Dr. Nadal, because I write down on whiteboard.
Dr. Ahmed, maybe we'll add something, or?
Yes, please. So I'd just like to add something on the comment given by Naima in the chat. Yeah, I do agree that education is important, and we have to. One thing is we have to also look how we actually deliver this kind of information, because I think it's a good question to ask how many of our students actually go and look at those vernacular architecture of Oman. And this is a good question that can be asked to students, it's whether it's students at school years or whether it's at the universities. And so we have to take them out. You have to take the students out. They can do experiments. They can learn themselves. And I think there is no harm in learning from the architecture around the world. However, when we learn something, we have to ask these kind of questions. Why are they done that way? Because what's what's acceptable for one environment could not be useful for another environment. And so we always have to kind of raise this kind of question. Yeah, so I think that's all I wanted to say, Dr. Nawaf. Thank you.
Okay, let me go to the second question to Dr. Isipio. There is a question related to in the evaluation of PMV, what are the indoor air temperatures of the 3 scenarios that you are using in your case study?
Thank you very much for your question. So in the numerical simulations, the program calculates all variables in each space. So the program calculates the indoor air temperature, the evolution during the day. Using the air temperature and the water concentration in the air, the program calculates the relative humidity. The mean radiant temperature is calculated using the surrounding surfaces, the mean value around the surrounding surfaces. And the air velocity is possible to calculate use previous data of the CFD. So in this case, the numerical software calculates the evolution during the day of the air temperature of the space, the mean radiant temperature of the space, the relative humidity, and the air velocity, and use the activity and clothing level. So using these informations, the program calculates the PMV.
Related to the indoor air temperature itself, have you fixed something related to code, maybe ASHRAE code or something like that?
Yes. So there are for each space, the program developed one equation for each spaces in order to evaluate the indoor air temperature that consider the heat exchange between convection, radiation, and all phenomena inside the space. These equations is used to evaluate the indoor air temperature.
I see. Okay, thank you very much. Let's move to another question to Dr. Sayed. In fact, I have seen that the sample of the participation, they are just maybe 5+7, which consider maybe in research is very small participant. Is there any, especially I mean in the corona pandemic case, so a lot of people, maybe elderly people, are sitting at home. So why the participation are very low?
There's many reasons. Initially, we had a lot more participants. For the care home study, there was going to be a follow-up one. However, COVID restrictions didn't allow us to take more measurements from the care home itself. Secondly, with the home office study, to ensure measurements were taken from a distance without participants, interacting as much, it was quite tricky to ensure that like time schedules and things go into place. Plus, Sweden's lockdown ended midway through the actual participation, so finding participants who were still working from home was not as easy as possible. Again, also, this research was for my undergraduate dissertation, so I had quite a limited amount of time being an undergraduate student.
I see. Okay. One more, in fact, maybe suggestions related to new technologies that maybe are smart application that may be used for controlling maybe the indoor air temperature for elderly people, according to your data. Is there any idea about using this new technologies to help this people?
Oh, I feel that the technologies stated from the question, it could be utilized to benefit the elderly and other participants. What the main purpose of this study was to see applying what people have found to work quite well into an environment where people are interacting normally. A lot of the studies we found, people were doing it in climate chambers, and that affects how people psychologically respond to responses. And we wanted to see initially how people react in their current environments and what could be done with machine learning in the future. So the purpose of this was see if theoretically, the limitations of taking biometrics using thermal imaging, etc., and what could be done to improve it for potentially a future study where a machine-based learning could be used to adjust the environment in accordance.
One more question goes to the first presenter, Dr. Ahmed. According to the data you have provided or the literature review, artificial intelligence and Internet of Things need consider a new technology, so it requires maybe infrastructure. Do you think Oman in the near future has this kind of infrastructure and capabilities to this transformation for energy and zero energy buildings?
Yeah, I will start by saying something. Actually, the telecommunication company already put a lot of investment into the infrastructure. For example, company like Ooredoo to spend money on LoRaWAN, and they've already starting, using this infrastructure in different applications. Omantel also has done that. But to be honest, just having the normal networks actually allow us to do a lot of data monitoring remotely without any problem. For example, using the current networks like the GPRS, which is the 2G, to the latest, which is currently the 5G network. So that's absolutely not a problem in terms of communication. In terms of hardware, there is also a lot available. It's not a problem to do that. But these kind of components of the infrastructure is not the only thing. It's just actually provides you, like we say, it's just the base. These are the tools that you have to use. But then you will have to take these to the next level, where you collect the data and analyze them, and then also do the research on how you can apply the control algorithm. If you do the control or if you monitor them, then you have to analyze the data. So that's where actually most of the work that needs to be kind of focused on. The infrastructure is available.
See, that's really interesting. So, Dr. Abdullah, maybe if you can add something, or is there any other questions?
I have just one question from my side to the second presenter about, he put one as an input for his model about the carbon dioxide concentration. I don't understand how is this affecting the radiation and others. If you can delete it from the model, what's the effect on the result?
The question is the influence of the solar radiations of the carbon dioxide concentration.
If we delete this item from as an input, this carbon dioxide concentration, will affect the result and the temperature profile?
Yes, there are two kinds of situations. The software calculates the middle value of the carbon dioxide concentration. I use the mass equations, and I use the inlet and outlet and generation carbon dioxide concentrations from the peoples. So using these informations, I can evaluate the distribution or the evolution of carbon dioxide concentration inside the space. I use the ASHRAE standard 55, and the limit, it's around 1,800 around this value. And if the value is higher than the limit, so the indoor air quality, it's not acceptable. However, if the values of carbon dioxide concentration inside the space is lower than the limit of the ASHRAE proposed, so the air quality is acceptable. This is one step. Another is using the CFD with the people, and then I can evaluate the carbon dioxide concentration in the respiration area. So this is a similar philosophy that I use in the paper that I presented yesterday. And using this philosophy, I can evaluate the air quality using in detail the occupant distributions. In this paper today. So I use the middle value of the carbon dioxide concentrations to evaluate if there is acceptable the air quality using the reference value.
Thank you very much. I think we don't have a question. I don't know, Naval, if you have any additional question to the
Thank you very
presenter.
much. That's all from my part. Maybe if there is any other questions, maybe we have to end the session.
If the presenter number one has the question to the number two, is also possible to highlight your question.
That will be fine.
Okay, thank you very much, and nice to listen to this nice all presentations and topics recently active in thermal comfort, and hope to meet you again physically in another event, and wish you all the best. As I mentioned, the record presentation will be delivered later on. Thank you very much.
Thank you.
Thanks.
Yes.
Thank you so much.
Thank you very much.
Thank you.